Good afternoon, everyone. Welcome to today's webinar hosted by the NOAA Central Library. The library's seminar program provides an educational forum for the presentation of ideas, research updates, and news in support of NOAA's mission. I'm Katie, and I'm excited to invite you to another of our NOAA Innovators presentations. Please note this presentation is being recorded, and your name, email, and questions will be shared with the presenter after the seminar. As an attendee, you are muted, so please place all questions in the question panel and note that we do not have a chat function, only questions. So anything you ask will be asked of the speaker at the end of the presentation. And if you have technical issues, such as no audio or visuals, please try logging off and back on, as that solves most issues. It does not solve all issues, and you can always chat me to, or send a question, so I can help troubleshoot that. And with that, I'm going to turn it over to Tiffany House to introduce our speaker today.
Thank you, Katie, and welcome everyone. Again, my name is Tiffany House, and I am the Commercialization Specialist of the NOAA Small Business Innovation Research, or SBIR program. Welcome to the NOAA Innovator Series feature presentation. This series features innovators who have developed highly innovative products and services that advance NOAA's mission. Speakers include NOAA scientists and engineers, as well as entrepreneurs who have participated in NOAA's SBIR program. Inventors highlight novel features and potential commercial applications of their inventions and share insights on their experiences transforming creative ideas into technologies that solve real-world problems. The technology you will hear about today is currently in Phase 2 of the NOAA SBIR program and is available for Phase 3. Now, Phase 3 is work that derives from, extends, or completes an effort made under prior SBIR funding agreements, but is funded by sources other than the SBIR program. Phase 3 work is typically oriented towards commercialization of SBIR research or technology, including further R&D work. Once an agency determines if the SBIR company is available, capable, and willing to perform the work, an agency may award a Phase 3 through a sole source procurement. I would like to take a moment and introduce our speaker, Dr. Matt Brown. Dr. Brown is a principal engineer on Kitware's computer vision team located in North Carolina. He has over 12 years of experience developing advanced imaging systems and image exploitation algorithms. His expertise spans from the fundamental physics of imaging to the applied aspects of designing and integrating hardware and software to solve challenging problems. Ladies and gentlemen, I give you Dr. Matt Brown.
Thank you, Tiffany. Today, I'm excited to present some recent work funded by a NOAA SBIR grant to develop a general purpose drone payload to support data collection and real-time processing for beyond line of sight operations. This work was done in collaboration with the Aquasi Group from the University of Alaska Fairbanks to support NOAA's call for drone sensing and processing technologies to help them expand their existing drone operations to support beyond line of sight capabilities. My co-PI, Peter Webley of Quasi, is on the call as well. So for the scope of this Phase 2 effort, we've focused on a specific mission of monitoring the state of ice within frozen rivers to better understand their evolution, as well as better predict when a catastrophic flooding event may occur. And we'll cover that more in a moment, why this is an important mission and the progress that we've made on this project. But I think the larger, more important story here is what's next for our system. So I want to also highlight the really interesting general capabilities that we've demonstrated and how these can support a much larger set of missions. I will also point out, I'm not sure if you can see my cursor, but along the bottom here, as well in the chat room, you can see the website for this project, and I encourage you to check that out. So we call this system the Adapt Multi-Mission Payload because our long-term goal is to develop it into an open source general purpose foundation for a wide variety of end user missions, a number of which are shown here on the slide. For example, you could fly an algorithm that automatically segments and detects the regions of flooded water in the imagery that you're flying so that in real time you can map out flood regions and provide real-time feedback to emergency service personnel where they could drive, where they could navigate. A similar situation for monitoring forest fires as they evolve, oil spills, person search and rescue, and there's a common theme in all of these that swapping in the appropriate deep neural network for that type of computer vision is all that's needed, and then this back end of capability with geo-registration, dissemination of the results over a wireless link, and then passing these results on to decision makers. So there's two main threads of utility that this payload provides. One is raw data collection, helping people collect better data, and the data that you actually need to support training these models. And it's a framework that gives you quality control into that data, even when the system is beyond line of sight. And then, as I mentioned, for these disaster relief applications, where it's crucial to draw insights very rapidly, deploying this deep learning on board the system itself is really a major capability. So we aren't the first to apply deep learning computer vision to drone imagery or even to deploy real-time vision in flight. This has been a pretty active topic within the recent years in the academic literature, and there are even startup companies sort of devoted to this. But what makes our work hopefully more impactful than this existing work is our focus on releasing all of our outputs as open source, trying to seed and support an enduring open source project. And if you look at the explosion of success in AI as a whole over the last decade, it's largely a story of open source software. From general computer vision tools like OpenCV to standardized deep learning tools like PyTorch and TensorFlow. In all these cases, you have an initial organization backing the initial standardization to an extent of these tools, and it's just allowed lowering of barriers across the board and a lot of really exciting stuff. So the company I work for, Kitware, is well known in the open source community. We have a wide number of widely used packages and toolkits across a number of different domains. And so as an organization, we have the backing to really maintain something like this longer term going forward. I am in the computer vision group, and in our group, we pretty much tackle any of the prominent computer vision threads that people are exploring today, from analysis of forgeries to object detection, tracking, 3D reconstruction. So we also have, that large expertise. We're very active publishing in a lot of impactful journals like WACV and CVPR. So we really have that backing to kind of continue to contribute. And we also, on this project, we've been working in collaboration with the Aquasi group, who brings pretty extensive years and years of expertise deploying drone systems in challenging environments. So as I mentioned, the development of the ADAPT payload is supported by a NOAA Phase 2 grant, which we're about halfway through our 2-year schedule. And on this effort, we focused on the specific mission of monitoring frozen rivers to possibly be able to better predict when ice jams may occur. Here we can see some details of the 2013 Galena flood, which occurred due to an ice jam on the Yukon River, which caused extensive damage, both in terms of dollars and disruption of livelihood. So we took inspiration from similar NOAA-funded work by our collaborator, Aquasi, from 2017 to investigate the effectiveness of drone surveys of ice conditions on the Circle River in Alaska. And that work showed that drones can be really effective in collecting the requisite data, but it also pointed out some bottlenecks in the process, particularly related to the dissemination of the data, how long it took to get it off the UAV, to subsequently process it, and then disseminate it to stakeholders, given your, this data is collected well away from, major centers, and so the time that it took just to disseminate. So the question that we asked is whether real-time deep neural network computer vision could be applied on board the UAV itself to distill down the critical essence of the river state, and then only those summary analytics needed to be transmitted wirelessly to a ground station and then beyond. And we envision the ADAPT payload supporting an iterative workflow, as you can see shown here on the slide, where the system actually helps you collect better data. It aggregates and curates the data, the metadata, the imagery. It helps you integrate it with do-it-yourself deep learning tools such as Viame and another product, open source toolkit that Kitware produces to train your model. This would be done at a desktop computer or on the web or in a server farm. Then you upload this model back onto the system, and then you're ready to go fly. And you continue over time as you collect more and more data. Even during missions, you can feed that back in and get better and better results. And what we're talking about here is segmentation of the river ice boundaries. So we're interested in whether semantic segmentation of the imagery can be used to distill out the critical features encoding the overall river ice state, because this is particularly compressible versus sending the raw imagery, massive amounts of imagery back to the experts. If we can, as you can see in the slide here, we can run in-flight scene segmentation, separating out where the frozen ice is, where fractured ice is, where regular background ground, liquid water is. And then these regions can be vectorized, compressed to, in this case, the example here, the full image itself is almost 2 megs, and we were able to get it down to 20 kilobytes. And this is really useful now when you're talking about the online site operations with a pretty low bandwidth comms link. And these results that you see here, this was from our phase 1 effort, where we actually demonstrated that this is possible in real time on a small embedded computer here, the NVIDIA Xavier. We've explored even smaller versions of this, but this was sort of the sweet spot for us. And as I mentioned earlier, a goal for the ADAPT payload is really to be something of a foundation that research groups and organizations can exploit as a really good starting point to continue their differentiating the system into their own specific use cases. And briefly here I'm showing one of the major outputs we're trying to produce. This is a snippet from the website where we've listed out all the components that we've used, where you can find them. We have documentation on how you actually put the whole system together, installation instructions for the software. Those aspects are really critical to getting started with a project like this. And so hopefully we're having some of our non-recurring engineering, throwing that out there for other folks to be able to latch onto. So here we can actually see the payload fully assembled with all of the major components. The camera is completely adjustable from forward-looking to nadir. The GPS INS provides payload geolocated pose. The carbon fiber shell you can see with the NVIDIA Xavier computer tucked inside, and then we have a wireless downlink. And one of the design goals was to maintain this as a relatively low-cost system. Again, so it's accessible to a very wide audience. And here are some images from our recent trip. 2 weeks ago, we just got back from Fairbanks, Alaska, where we deployed a flight test for this system. Of course, this is a warm weather flight, so it was a baseline for us. That's useful because knowing where the river normally is under normal conditions is very useful during exploitation in frozen weather, to know where you might expect it to be, and that helps with the inference. These flights were on the Tanana and Chena River in Fairbanks. So these floats were focused on demonstrating functionality. Increase the resolution here. And here's a live view. This is actually a screen capture, the left portion here, of what we were seeing live on the laptop while we were flying. After the fact, I superimposed in what I took with my cell phone on the right here. But it's showing live operation and the utility of the feedback you get. This is a very low latency, compressed, low bandwidth view of the system live, and you can see the deep learning being deployed on the system, but you get a sort of a sneak peek back at the laptop, and you can assess where the payload is on a map. This model that we deployed is not our ice segmentation model because it wasn't snowy or icy. This is a model we trained using AirSim, but it sort of proves the point that we can, it's the same size model that you would run for our ice segmentation work. And so it proves the point that you really can run this in real time and get usable results. And so a little bit of a deeper dive in some of the capabilities where you might see that this is useful for research groups really trying to collect very good data. A lot of times you find you go out to these events, you do a long day collection, you take all the data back to the hotel, and you realize that it wasn't quite how it wasn't configured properly, and you've sort of wasted a whole day. This is actually a live feed from the system that we're interrogating the operations. You can see the histogram here. This is actually when the system was about 2,700 feet away, right at the edge of beyond line of sight. So it's still within sight. Just because for simplicity, we didn't go for the full beyond line of sight certification for these test flights. But what you can see here is actually a live inspection at a very high zoom. The top view is a global view, and the lower view here is 100 to 1,000% view, where we can verify that the imagery is sharply focused, it's not motion blurring, all of the sanity checks are there. And again, this is, we're right at the edge of beyond line of sight. There was nothing about the system preventing us from going to beyond line of sight, other than for this particular flight, we did not get the certifications to go fly beyond line of sight. Aquasi has as an organization has certifications to be able to do that with this particular flight for simplicity. So another, one of the areas we really focused on is the quality of the data you're getting from this system, particularly in terms of synchronization between the inertial measurements and the imagery. I won't go into the details of exactly what these plots are showing, but they represent the alignment both from the imagery derived motion and the inertial motion. Effectively, if you look at the imagery, you can tell how you're rotating from a structure for motion sense around the camera's coordinate system, and then as well, the INS tells you how it's moving. The fact that these line up perfectly is a huge sign that we've gotten it right in terms of temporal synchronization. This is something that people that research simultaneous localization and mapping, the SLAM community, put a substantial amount of effort into, and it often involves these very custom Arduino configurations. And so our hope here is, again, this is a foundation where much more easily somebody could have a system with this type of capability. And what that means is you can do more mapping operations, more geospatially aware analysis much more easily than otherwise. And here, case in point, is an example where that geospatial awareness really pays off. These are comparisons between days. This is Circle Alaska data previously, but we're using the same processing to exploit it, where each of these images is made of a composite of hundreds and hundreds, 600 images or so, to build them together. And they were processed simultaneously in a structure for motion, so that they were all co-registered. So within a day, it's much more easy to co-register. Inter-day, the process latches onto features, such as these very stable regions here. And what that means is you can actually propagate registration into regions where they are very dissimilar. So in this inset region, you can see this is what the ice looks like 3 days prior, and so you can do very precise change detection precise in a geometric sense, which is really useful as you analyze the progression of the environment. So taking a look at some of our ice segmentation results, in this work we're running a BICENet v2 segmentation network. This is specifically chosen because it is top state-of-the-art for real-time processing operations. We can run in real time on our NVIDIA Xavier. We get about 2 to 4 hertz depending on sort of quality levels that we assign to it. And we've spent a lot of time and effort annotating the data so that we can tailor-make a model for this process. There really has been relatively limited work in the open source for ice segmentation model training, and so putting together this data set is a critical aspect of our workflow. And we've also exploited a pretty novel annotation workflow where we're exploiting the AI itself during the annotation process. And for example, what's going on here is you start with this training image and you sparsely annotate, very quickly in some of scribbles. You can see these regions here. We've loosely scribbled in the classes that we care about. Ultimately, we care very much about the intricate boundaries because that tells us a lot about the state of the ice. And after you have some subset of your data that you've annotated in this way, we train the model and we let it interpolate within those data sets. And here you can see what the model did to interpolate for this particular image. You still have to go back with the annotator and validate that interpolation process. But what you find is that letting the model take a guess and then tweaking it is much more efficient than actually going in and verbosely annotating. So here you can see the model suggested this segmentation. We went in and we quickly corrected it. And now we have a very fine and intricate annotation for this image that we can feed back in into the overall training. And once you've validated all of the machine suggested annotations, then we can train the full complete model. And here's some just more visualizations of what that ice segmentation deployment looks like on real ice data. Again, this is Circle River data from 2017. We have yet to hit our winter flight on this project. We started just after the project, just after the winter thaw from 2021, and so the winter of 2022, we're going to deploy in the field and really show the capabilities for this particular mission. And so I would like to thank NOAA for funding this work, thank our collaborator, Peter Webley of Aquasi, and I'd be happy to take any questions. And again, if you're interested, please check out our website shown here on the bottom as well as in the chat room.
Great, thank you so much, Matt. I'm going to give everyone about 30 seconds to get those questions typed in, but I'm going to turn it over to Tiffany to see if she has any questions to begin.
I do. Thank you, Katie, and thank you, Matt. I did not hear any discussion on who the customers would be, and also I was wondering if you could go back into the applications for this technology.
Sure. So customers can span a pretty wide gamut, and we're sort of taking example from the work that Kitware kind of tends to do in this similar space where we're developing an open source system. That's a pretty common question. How do you as a company monetize an open source system? What we find is that it's split across commercial organizations, government organizations, government projects, and even some interest from research groups. The way Kitware typically monetizes that is we put the system out there as available. It becomes adopted highly, and then folks are interested in either us supporting them in training a model, leveraging our deep AI expertise in really optimizing their use case, both in training as well as any modifications to the system or the software. So in terms of applications where I could imagine this could be very useful, oil companies that are dealing with an oil spill, you could send this system out there and monitor the progression and have better real-time feedback and updates on what's going on. Certainly possibilities from NOAA itself, monitoring forest fires, monitoring disaster-related events, floods, person search and rescue, any of these domains where you simply just need to train a tailor-made model for your particular application.
Thanks for going over that again, Matt. And what do you need in order to reach your goal? I know that right now you have the funding from the SBIR program. What else are you looking for? Are you looking for partners, additional funding, outreach?
I think we're definitely open to all of those things to reach our goal. We would love anybody interested in partnerships. Help collaborating to customize the system for their specific mission. We're really looking for somebody who has a domain problem where this system could be kind of a unique solution for them.
Okay, Tiffany, if that was the end of your question, we do have another question in the question panel. So Matt, does running an onboard GPU drain the drone battery quickly?
It certainly drains it faster than otherwise. In our missions, we get about 20 to 30 minute flight time. These are we have two 2200 milliamp hour batteries. So there definitely is a reduction in flight time, but it is not something that precludes viability of these type of operations. And the system, so what I would say that the more interesting parts of the system aren't really the carbon fiber pieces that we've put together, the actual, the way we've laid this system out. It's really in the software and the system integration and tackling the hard parts of those components. So you could equally, without too much effort, imagine packaging this system up into the cargo bay of a much larger UAV, like a fixed wing system, and supporting much longer flights where the power limitations are a little bit looser.
Okay, good to know, because that was the second part of the question was, are complex models constrained by the power requirements?
So if you just go look for state of the art, what is the best model that you can run for the problem, those would be constrained by SWaP, our size, weight, and power. If you can take a little bit of hit off of that state of the art in performance, maybe 10% reduced accuracy, then you're starting to see the realm of these models that people are developing specifically for real-time operations. And those models are getting better and better every day through a variety of optimizations during training. And so it really is an exciting opportunity at this moment to start exploring some of these deployments.
Great, thanks, Matt. That was the one question we had in the question panel, unless someone is typing furiously. I don't have anything else. Tiffany, do you want to highlight the next upcoming NOAA innovators, or do you have a follow-up question?
We actually have one coming up in October. Let me get the date. Oh, the next one is coming up October 26th. That's our next innovator series. Matt, I did have another question.
Sure.
How did you come up with this idea?
Sure. So there are a number of different inspirations for the idea. A lot of so Kitware, the computer vision group, does quite a bit of work in the defense space, and so we do similar work with deploying and developing fielded hardware, much like this. And so one of the things we're really happy to do at Kitware is, because we're an open source company, and on the defense side, we always strive to get as much of the work we do on those programs open sourced. It's an opportunity for us to bring in technologies that were developed on these large budget defense projects and transition them into more of the science geared, the NOAA projects. Kitware has a large embedding of use in the NOAA fisheries offices using Viame. As I mentioned earlier, it's a do-it-yourself training algorithm system for training object detection and classification. And how it gets used in NOAA is that they're responsible, in these fisheries offices, are responsible for monitoring population abundance estimations. And so over time, that's gotten more sophisticated, from just pulling fish on a deck and sorting them, to taking pictures underwater. And now we're actually having a domain expert train a model by annotating the different species of fish in different images. And then once you get to sort of a critical level of annotation, now you can just deploy your trained model on your data with relatively high confidence that it's going to make the correct assessments each time. And so Viame as a whole is used pretty heavily. I worked a similar project with the Marine Mammal Lab out of Seattle, NOAA Fisheries Office, and their charge is to monitor populations of Arctic mammals, so seals and polar bears. And they put together a camera system it's a 9-camera system with 3 IR cameras and 3 RGB cameras and 3 UV cameras, 3 co-bore-sighted triplets. And so I worked on a project with them to actually build a much larger version of this system, trying to achieve much more because of the volume of imagery that's flowing through. And we deployed real-time in-flight seal detection, and that was really useful for them, along with the quality assurance components to viewing it live, so that once they landed, they have a very good feel for how successful the flight was, what they saw, how they need to revector for the rest of the week. And so that work, transitioning into this, I sort of envisioned this as the miniaturization of that other work, and also making it a much more generalizable and cross-deployable.
Thank you,
Okay,
Matt. And Katie, I don't have any other questions.
great, because we do have a few more questions that we're going to grab here. First is a great briefing, Matt. I see your payload solely utilizes color imagery. Do you have plans to incorporate multispectral, such as MicaSense red edge cameras, into future payload configurations?
Yes, absolutely. As I mentioned on the other NOAA project, we worked with 3-band, RGB plus UV and IR, and there's sort of no reason not to be able to exploit those additional sensors. It would just be a camera integration exercise, and it would leverage a lot of the same work that we did on this project to get that underway. That would certainly be a great opportunity. And the deep learning itself and all of the tools we use for training can support multimodality fusion. On that other NOAA effort, the goal there was to actually fuse RGB, IR, and UV into the same image space, and so do multimodal detection fusion.
Great, thank you, Matt. Our next question is, What type of data is collected on flight? Could it be used to monitor spot fire, wildfire, and perform an in situ evaluation that can be shared real time with the firefighters for best strategy? How easy was this to swap the AI?
So swapping the AI from one angle, if you have the model, the swap is very easy. We're leveraging a lot of tools that we developed in-house to make, Viame is actually one of those tools. It's both the training part as well as the deployment part. But if you have the model, it should be very easy to swap it in. Generating that model is potentially more work, but that's where the payload can actually help you collect good data that is actually geo-registered, and you can get good scale from that. Integrating a different modality camera, like an infrared camera, would make a lot of sense in that application, and that initial integration exercise shouldn't be too hard, again, since we can leverage a lot of sort of the pain that we underwent on this project for initial integration. For example, it should be pretty easy to tell where the fire boundary is in the infrared, and so that should be a very exploitable problem from a deep learning sense.
Thanks, Matt. I think you answered that first question then about what type of data is collected. It seems like it depends on what your model is looking for.
Yeah, so more specifically, we focus mostly on image-based data. There's no reason you couldn't add additional sensors, temperature, other factors that could be combined into the system. But primarily, we're interested, at least on this initial effort, on image-based data.
Great, thank you. That seems to be the end of our questions for now. And as Tiffany mentioned, there will be another NOAA Innovators seminar coming up in October on the 26th. Please be on the lookout for that. But if you don't have any other questions, we will end our seminar for today. Thank you so much, Matt. Thank you, Tiffany.
Thank you.
As a reminder, this was recorded, and if you want to watch this again, if you want to share it with a colleague, it'll be up on the library's YouTube channel. There is a playlist for the NOAA Innovators. Thank you all for coming, and I hope you have a wonderful rest of your Tuesday. Be safe out there.